As you watch this video, one of Europe's most dangerous volcanoes is quietly disintegrating. This isn't about fleeting cracks that appear and vanish. Rather, an entire side of the mountain is gradually slipping into the sea. Alarmingly, scientists warn that this process is accelerating. Sensors placed along the volcano's slopes have detected a disturbing development. A massive rocky section, weighing billions of tons, is detaching from the main body of the mountain. Initially, this movement was measured in millimeters per year, seemingly insignificant, but over the past decade, the rate has increased dramatically. Currently, certain areas shift by centimeters each month, transforming what was once a slow landslide into a full-scale volcanic collapse. When such large volcanoes like Etna break apart, the consequences can be catastrophic. Imagine a colossal mass of Earth suddenly plunging into the ocean, displacing water with immense force. This triggers towering waves, sometimes reaching dozens of meters in height, racing across the Mediterranean. Coastal cities could be submerged within minutes, with the destructive waves spreading to Greece, Malta, and even North Africa. Millions of lives could be at risk, yet such warnings often go unnoticed until it's too late. But what causes this mountain to disintegrate so dramatically? Each centimeter of movement increases the likelihood of a more powerful and unpredictable eruption. Since the debris is moving toward the sea, scientists fear that a major landslide could cause a volume of rock so vast that it generates a tsunami capable of devastating entire coastal regions. Evidence of this danger has been mounting. In 2017, research teams from Germany and Italy took an unprecedented step. They deployed sensors on the seafloor beneath Mount Etna, at depths exceeding a kilometer. Their findings were startling even to themselves. They discovered that the entire structure, not just the surface, was creeping toward the ocean. This indicates that gravity and magma pressure are working together to destabilize the volcano. Since then, earthquakes along the slope have become more frequent. Not random tremors, but cracks under tension. Signs that the volcano is literally falling apart. Satellite radar has captured deformation patterns consistent with early stages of a major eruption, but not from the summit, rather from the mountain's flank. This pattern mirrors the catastrophic event of 1669, when Etna's southern slope suddenly erupted in a series of deep tremors. Without warning, the earth cracked open far below the summit, unleashing rivers of flowing lava that consumed everything in their path. The eruption lasted 4 months, destroying over a dozen villages and reaching the city of Catania, where homes, churches, and roads were buried beneath a sea of molten rock. Recent months at Mount Etna have raised concerns about a potential new eruption cycle. On June 2nd and 3rd, a powerful eruption struck the southeastern crater, causing part of the crater to collapse. Explosive bursts followed one after another, sending ash clouds several kilometers into the sky, while streams of molten lava flowed down the slopes. Videos of the event flooded the internet, captivating viewers with their awe-inspiring yet frightening spectacle. Authorities responded immediately by raising the aviation alert level and closing areas around the summit to tourists. The Catania airport periodically halted operations due to ash fallout. Monitoring indicated that, despite the dramatic display, the eruption remained relatively safe for nearby settlements, as lava stayed confined within natural barriers of the volcano. Interestingly, seismic activity radiated outward towards surrounding towns, prompting many tourists and residents to evacuate from the slopes. However, the unrest did not subside. Throughout July and early August, activity intensified. becoming more persistent with frequent eruptions and continuous lava emissions from multiple craters. Satellite imagery revealed significant thermal anomalies, and cameras operated around the clock. By mid-August, observers noted a new surge in activity. Explosions grew more powerful, short-lived lava fountains appeared, and new fissures opened on the slopes. Then, an event occurred that further alarmed scientists and experts. Between August 20th and 23rd, a fresh lava flow emerged on the southern flank of the eastern craters. Drones and geologists documented the flow's expansion and increased activity in the affected zone. Authorities responded by tightening restrictions again, as lava reached lower elevations than usual, and roads experienced landslides and heavy ash deposits. Satellite data confirmed rising thermal anomalies, indicating an escalation in eruption strength. Around September 22nd, a notable spike in activity occurred, marked by explosive eruptions and intensified volcanic behavior. Nighttime lava fountains, seemingly originating from the coast, illuminated the landscape. Geochemical laboratories analyzed samples from a unique eruption that took place approximately 3,100 years ago. Back then, Etna erupted a rare and primitive type of basaltic magma known as picrobasalt, with an explosivity index of 4, comparable to the recent eruption of the Icelandic volcano Eyjafjallajökull in 2010, which caused widespread air travel disruptions across Europe. This ongoing series of events underscores the volcano's volatile nature and the importance of continuous monitoring. In ancient times, scientists isolated mineral inclusions from deep-seated rock formations, tiny fragments of natural magma trapped during crustal reworking. These inclusions act as microscopic time capsules, preserving a record of geological processes from thousands of years ago deep within the Earth. When subjected to experimental heating under immense pressure and temperatures reaching up to 1,330 degrees Celsius, researchers uncovered startling facts. The original magmas contained up to 1% carbon dioxide and 6% water, astonishingly high concentrations. The question arose, where did all this CO2 originate? Previously, it was believed to come from carbonate-rich sedimentary rocks beneath volcanoes, ancient marine deposits melting and releasing gases. However, recent studies suggest a different source. Evidence points to mantle-derived carbon, likely originating from the Earth's deepest layers, indicating a mantle source rather than crustal sediments. Further calculations revealed that magmas rich in CO2 and water began crystallizing at depths exceeding 30 kilometers. Below the Mohorovičić discontinuity, the boundary separating the crust from the mantle. This provides direct proof of the mantle origin of Etna's magmas. Even more astonishing was the estimated ascent time of these magmas. Through mathematical modeling, scientists determined that mantle-derived magmas could reach the surface in as little as 2 to 5 days, with the fastest stages taking merely 2 to 3 hours. The final 15 kilometers of ascent occurred at an average speed of about 1 kilometer per minute, 17.5 meters per second, an incredibly rapid transit. Essentially, magma is propelled from the mantle like a projectile, driven by the enormous pressure exerted by high concentrations of CO2 and H2O. This explains the catastrophic nature of ancient eruptions and raises concerns that similar conditions could be forming today. Another study revealed that presently Etna emits an extraordinary amount of CO2, around 10% of all volcanic carbon dioxide emissions worldwide, approximately 9,000 tons daily. This is 3 times more than Kilauea, which, despite erupting 4 times more magma, releases significantly less CO2. The discrepancy was traced to the unique composition of Etna's magmas. Analysis of rare element ratios in magmas from regional volcanoes showed that Etna's magmas have exceptionally high levels of niobium to tantalum ratios, higher than any other active volcano of its type. This indicates the presence of highly carbon-rich regions within the Earth's lithospheric mantle beneath southern Sicily, at depth between 50 and 150 kilometers. These zones are transported upward by tectonic activity and the subduction of the Ionian plate, revealing a dynamic mantle environment rich in carbon and capable of fueling such intense volcanic activity. In simpler terms, tectonic activity in the region continually shifts magma beneath the volcano, which could lead to increased sulfur dioxide emissions from Mount Etna in the future. Besides periodically sliding into the sea and erupting with lava fountains, the volcano exhibits another peculiar trait. Its crater constantly shifts position. Unlike most stable volcanoes where the vent remains fixed, Etna's vent seems to wander from one spot to another. Since 1971, the main crater was located in the southeastern part, but in 2007 it moved southeastward. By 2011 it shifted just a few meters from its previous position. Why does this happen? A detailed study of 6 eruptions, including one in 2007, revealed the answer. Volcanologists mapped the density of rock surrounding the vent using satellite data and geological excavations. They found that the rocks on the northwest flank are highly unstable and periodically slide downward, causing the vent to migrate. This process correlates with the increased frequency of eruptions during the latter half of the 20th century. More eruptions deposit additional lava at the summit, increasing pressure on the slopes and prompting the vent to shift. This phenomenon ties into the broader issue of gravitational movement. For a long time, scientists believed that volcano movement was driven by the expansion of the magma chamber. Magma filling the chamber before an eruption, causing the walls to rupture under pressure, leading to an eruption. This straightforward model, however, doesn't fully explain Etna's behavior. In 2018, researchers deployed underwater transponders around the southeastern flank of Etna, the side gradually sliding toward the sea. These devices, equipped with pressure sensors, monitored tiny movements at depths of 1,200 meters below sea level, 12 kilometers from the coast. Data collected from April 2016 to July 2017 revealed something unexpected. The underwater slope remained stable for most of the year, but then dropped by 4 centimeters within a span of 1 to 8 days before stabilizing again. Interestingly, the greatest movement occurred at the base of the volcano, with minimal shifts at the summit. If magma movement inside the volcano were responsible, the pattern would be reversed, with the most significant shifts near the crater. Moreover, the displacement was concentrated along a single fault line in the sea, while near the coast it spread across 2 fault systems. This indicates that the movement originated underwater and propagated upward rather than from magma intrusions. Furthermore, during the 8-day episode, no earthquakes were recorded, suggesting the movement was not caused by magmatic activity. Instead, it was driven by gravity. The volcano essentially sags under its own weight. As eruptions increase, the mass of the volcano grows, intensifying this gravitational pull. The entire structure is slowly spreading under its own weight, with the process becoming more pronounced with each eruption. Bringing all these observations together, it becomes clear that Etna's behavior involves a complex interplay of tectonic shifts, gravitational forces, and unstable rocks. The volcano's structure is expanding outward from the summit in all directions, driven by the combined effects of internal pressure, gravity, and geological instability. This ongoing dynamic process explains the constant movement of the crater, the shifting of the vent, and the gradual destabilization of its slopes, painting a picture of a volcano in perpetual, subtle motion beneath the surface. A volcano's entire flank gradually slips downhill at an average rate of about 14 millimeters per year, yet the overall movement toward the sea amounts to several centimeters annually. While this may seem slow, the internal stresses building within the volcano are immense. What truly alarms scientists are the catastrophic collapses, massive sectors of a volcano sliding away in enormous landslides that have occurred on other volcanic slopes under gravity's relentless pull. Such events happen roughly 4 times per century worldwide, often resulting in devastating destruction. Recently, an Italian volcanologist stated that the southeastern flank of Etna is actively shifting, not if it will collapse, but when. The concern is that even minor tremors, magma intrusions, or heavy rains could accelerate this process, pushing the volcano closer to failure. A team of German researchers confirmed that the slope's movement is entirely driven by gravity, indicating that it is no longer solely caused by magma pressure, but also by the volcano's own weight pulling it downward. Authorities in Sicily have begun revising safety protocols and evacuation plans for communities living on the lower slopes of Etna. Yet, most residents remain unaware that the ground beneath them is inching steadily toward the sea, inch by inch. This slow-motion catastrophe could suddenly escalate from a geological curiosity to a full-blown disaster at any moment. Increasing volcanic activity, including more frequent eruptions, adds layers of instability to the already fragile and unstable slope. Over the past 50 years, Etna has been in a constant state of unrest, with eruptions ranging from Strombolian fountains and lava flows to ash emissions. Since August, activity has intensified further. While the world watches the spectacular eruptions at the summit, the real danger lies beneath. The volcano is essentially tearing itself apart from within. When the flank finally gives way, it will not be just another eruption, but a transformative event that could forever alter the region's landscape and safety. That is all for now. If you found this interesting, consider exploring further and following updates in our Telegram channel, where we also share engaging materials.